In this video, we will explore the conversion of context-free grammars to pushdown automata. We will demonstrate how every context-free grammar can be converted to an equivalent pushdown automaton that accepts the same language. Here's an overview of the conversion process. We start with a context-free grammar, which consists of productions with variables and terminals. Through the conversion, we transform this grammar into a pushdown automaton, which operates with states and stack operations. The arrow signifies the transformation from a grammar-based representation to a state-based machine. Let's look at the steps involved in converting a context-free grammar to a pushdown automaton. Step 1. Create an initial state and push the start symbol onto the stack. Step 2. Add production rules as stack operations. Step 3. Handle terminal matching with input symbols. And Step 4. Define the acceptance condition with an empty stack. Consider this example context-free grammar. The first rule states that the variable s can be replaced by followed by s, followed by b. The second rule states that the variable s can be replaced by epsilon, which represents an empty string. This grammar generates a language L which consists of all strings of the form a to the power n, followed by b to the power n, where n is greater than or equal to 0. Some examples of strings in this language include epsilon, ab, aabb, and aaabb. Let's identify the components of the pushdown automaton we'll construct. The set of states denoted by Q consists of Q0, Q1, and Q2, representing the start state, loop state, and accept state, respectively. The stack alphabet, denoted by gamma, includes the grammar variables and a bottom marker, Z0. The input alphabet, denoted by sigma, consists of the terminal symbols from the grammar, which are A and B. The initial stack contains the bottom marker Z0, with the start symbol S pushed onto it initially. Here are the transition functions for our pushdown automaton, represented as delta, which maps a state, an input symbol or epsilon, and a stack symbol to a set of next states and stack symbol strings. We have two types of transition rules: production rules and terminal matching. For production rules in state Q1, reading epsilon and encountering variable s on the stack, we can transition to state Q1 and replace s with ASB. Or we can transition to state Q1 and replace s with epsilon. For terminal matching in state Q1, reading terminal and encountering terminal on the stack, we can transition to state Q1 and pop a from the stack, replacing it with epsilon. Similarly, in state Q1, reading terminal B and encountering terminal B on the stack, we can transition to state Q1 and replace B with epsilon. Let's trace the execution of the pushdown automaton with the input AABB. Initially, the PDA is in state Q0 with input AABB and Z0 on the stack. It transitions to state Q1, pushing S onto the stack. Then it applies the production rule and replaces S with ASB, resulting in ASB on the stack. It then matches the first A in the input with the A on the stack, transitioning to state Q1 with input ABB and SBZ0 on the stack. It continues processing the input, matching terminals and applying production rules until it reaches state Q2 with an empty input and Z0 on the stack, indicating acceptance. Here are the key takeaways from this video. It's a systematic process. Every context-free grammar can be converted to an equivalent pushdown automaton using a well-defined algorithm. Grammar productions become stack manipulations in the pushdown automaton. The resulting pushdown automaton accepts the same language as the original context-free grammar. Acceptance occurs when the input is consumed and the stack is empty. This conversion bridges the gap between generative and recognitive models. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.